Okay, now today we will discuss LED interfacing. That is your second practical. We already covered the first practical, that is memory interfacing. Now this is your second practical, that is LED interfacing. Now this is your practical kit. Here this is the microcontroller, that is 8051, and surrounding to that there are various peripherals such as these are the LEDs connected to the microcontroller. This is a keypad. This is a keypad section, that is 4 by 4 matrix. Then this is the 7 segments display, that is 7 segments are interfaced with the microcontroller, LCD, ADC. In this fashion different peripherals are there, speaker is there. In this fashion number of peripherals are interfaced with the microcontroller, that covered in your second unit. And for today we will discuss LED interfacing. Is this LED we want to interface with the microcontroller, and we want to perform various tasks on these LEDs. First, LED is nothing but light emitting diode. Okay, when current passing through this LED, it emits the light source. Okay, now the LED we are not connecting directly to the controller, we are connecting through current limiting resistor, either 220 or 470 or 1 kilo ohms resistor you are connecting in between, which is working as current limiting resistor. Then next, now this is your LED, picture of LED now, and this is the symbol of LED. Now this LED having two terminal, one is a anode and second one is a cathode. Normally anode is connected to positive and cathode is connected to ground. Okay, now this LED having two terminal, anode and cathodes, and here bigger leg is represent as a positive terminal, means it is represent as an anode, and shorter terminal is treated as a negative terminal or cathode. Now next point is you can interface LED in two fashion, either in common anode configuration or common cathode configuration. Now first one is common cathode configuration, means this cathode is connected to ground. Now when you are connecting LED in this fashion to microcontroller, that time now our role is to turn on and turn off the LED. Okay, now to turn on the LED, microcontroller must send 1 here. When microcontroller pin outputted 1 on this pin, that time this is 1 and this is 0, and that's why current is moving from 1 to 0, means current is flowing from anode to cathode, and LED turns on, means it emits the light and it turns on. Suppose our microcontroller send here 0. At that point this terminal is 0 and other terminal is also 0. Both are equipotential, and that's why current will not flow, and that time LED remain off. In this fashion, when you want to turn on the LED, microcontroller must send 1 here, means 1 is on, and when microcontroller send here 0, that time LED remain off. Means under this configuration 1 means on and 0 means off. All of you agree for this point? Okay, then next, suppose you are connecting LED in other fashion, that is common anode configuration. In this case your LED is connected in this fashion. Here when you want to turn on the LED, your microcontroller must send here 0. Suppose this is 0 and other terminal is connected to VCC, and that time current is moving from VCC to ground, and that time current flow through the LED and LED emit the light and it turn on. Means here when you are outputted 0, your LED turns on. Whereas when microcontroller send here 1, outputted 1, at that situation this pin is 1 and other pin is also 1, both are equipotential, and that's why current will not flow and LED remain off. Means under this configuration 0 means on and 1 means off, whereas exactly opposite of this configuration. Normally we are using common cathode configuration, means 1 is for on purpose and 0 for off purpose. When this is 1, LED current will flow through the circuit and LED turns on. and when it is 0, both are equipotential, current will not flow and LED remain off. In our next example, we are using common cathode configuration where we are treating 1 as on position and 0 means off position. Then next, we know that in 8051 there are 4 ports, that is port number 0, port number 1, port number 2 and port number 3. All these ports are working as first function is always by default GPIO, that is general purpose input output port. Means all these port we can use to interface our input device or output device. Okay, and along with that they are providing other alternative function also. For example, P0 we are using to carry address and data bus, lower byte of address along with data bus, means these are multiplexed. Next one is port 1, they are just working simply function, that is by default GPIO. Port number 2, first function is GPIO and second function it carry higher address byte, because our address is 16-bit address. The address number 0 to address number 7 is coming here, whereas address number 8 to address 15 is coming on port number 2. Then port 3 working as GPIO and second function, each pin work individually. Okay, it's providing serial communication, it support the interrupt structure, it support the timer section, it support read and write action, etc. Okay, but now we are not concentrating on alternate function, we are focusing on first function, that is GPIO, that is general purpose input output. Okay, you can use any port as per your choice. All ports having 8 pins, and you can use that 8 pins for interfacing our input output device. Now our second practical is LED interfacing. LED is output device, means you want to interface LED with any port as per your choice. Okay, now this is the picture. Now this is a picture of 8051. There is 4 ports are there, that is port number 0, port number 1, port number 2 and port number 3. In this figure we are just interfacing LED to one of the port, that is port number 0. All 8 LEDs are connected to each pin of port 0. Port 0 having 8 pin, that is P0.0 to 0.7. All LEDs are connected to this through current limiting resistor, and other end of LED is connected to ground, means these LEDs are connected in common cathode configuration, because all these cathodes are connected together and it is connected to ground, and that's why these LEDs are connected in common cathode configuration. When you are connecting in common cathode configuration, that time 1 is for on purpose and 0 is for off purpose. Now first we will discuss generalized algorithm for LED interfacing. Now first step is, always when you turn on the controller, that time microcontroller will PC, that is a program counter showing the memory location. Always it's showing the first memory location, that is 40H. But at 40H there is a register bank, then bit addressable area, and 0030 onwards we started the scratchpad where we are writing our program and editing the program as per our choice, and that's why by default our program counter is showing which location, 40H, but we don't want to write there because that is the location for register bank. Okay, and purpose of register bank to hold the data, not to write the program, and that's why we want to jump to the scratchpad, and our scratchpad is started from 0030H, and that's why we are first step we are jump to which location, 0030H. Okay, after that in second step we are loading the bit pattern as per the problem statement. Just go through the problem statement, as per that problem statement just calculate the bit pattern and just hold that bit pattern into the accumulator. Okay, and then pass that, and then okay, first calculate the bit pattern, place into the accumulator, that is your second step. In the third step, move the content of accumulator to the respective port where LEDs are connected. Okay, means for example port 0, port 1, port 2 or port 3, whatever it is. Means pass the content of accumulator to respective port where LEDs are connected. Then give the delay, because the speed of controller is so fast and human being is unable to see that variation. Okay, to avoid that point, we are just introducing the delay in between, because human being want to see that variation. Okay, and that's why we are just giving the delay as per the problem statement. Then next, fifth step is load the bit pattern as per same bit pattern or different bit pattern as per the problem statement again. Then put that new bit pattern into the accumulator first, then pass that accumulator content to the respective port and then give the delay in this fashion, and then go back to the step number 2 again. Means you are remain in the loop, means continuously you are doing that action. In this fashion, generalized algorithm I just declared. Okay, now as per the problem statement, I will just make the modification within it. Now my first problem statement means we are just performing all this problem statement during practical duration. Okay, problem statement is to demonstrate the LED blinking or toggling with a delay of 1 millisecond. Means there are 8 LEDs, they are connected to the port number 2. Okay, and we want to blink the LEDs with the delay of 1 millisecond or toggle the LEDs with the delay of 1 millisecond. Means we want to turn on all 8 LEDs for 1 millisecond, and after 1 millisecond I want to turn off all 8 LEDs for 1 millisecond, and I will repeat this cycle. Means your delay LEDs will on for 1 millisecond, off for 1 millisecond, again on for 1 millisecond, and you will remain in the loop, and means it is nothing but toggling or blinking with a delay of 1 millisecond. All of you agree for this? And that's why we want to turn on all LEDs. Means 1 means on and 0 means off, because our LED you are connecting in common cathode configuration, and that's why 1 means on and 0 means off. Now in first task we want to turn on all LEDs, and that's why we are just passing all ones. All 1 means 8 1 you are passing, means it is FF. After delay you want to turn off all LEDs, means you want to turn off all LEDs, means you are sending 0 0 0, and that's why you are sending all zeros there to turn off all 8 LEDs. Now this is my problem statement. According to that I will just make changes within the basic algorithm of LED. Basic algorithm remain as it is, only as per the problem statement you are just making the changes. Now first step is same, that is initialize program counter to 0030H, because initially it is started from 40H. We don't want to write there, we want to write in a scratch pad, and that's why we are jumping on 0030H. Next step, that you load the bit pattern as per the problem statement. In my problem statement, what would I want to blink the all LEDs. Okay, that's why initially I want to turn on all LEDs, and that's why I'm passing 1 1 on each pin. On each pin, that is P 2.0 to 2.7, I'm passing 1 1 1. That's why all LEDs will turn on. This all 8 1 is nothing but your FFH. But we can't directly place FF directly. We must pass with the 0, because it is started with the alphabet. And that's why I am placing hash 0 FFH into the accumulator in the second step. In the third step, I will just pass the content of accumulator to respective port, that is port 2. Then I will just give the delay as per my problem statement. Then load different bit pattern. Now what I want to blink. Okay, and that's why I want to turn off all LEDs, and that's why I am sending 0 0 on each pin, and that according to that my number is 00H. That I will first place into the accumulator, and then I will pass to the port. then I am just giving the delay of 1 millisecond. Means for 1 millisecond my LEDs remain on, after that 1 millisecond it remain off. Again go back to step number 2. In 2 again I am placing here FF, means again it will turn on, pass to the port and delay. In this fashion my LED remain on for 1 millisecond, off for 1 millisecond, and it is continue. Now as per this problem statement I am just converting one to one into the code. First step is what? Jump to the scratch pad, and that's why sjump main, and main jump is written at org is nothing but origin 0030h. Okay, from main function. Second step, in second step what we want to turn on all LEDs, and that's why my bit pattern is FF, but we can't write directly FF, and that's why we are writing hash 0FF inside the A accumulator. Then that's why I am writing move A comma hash 0FFH. After that whatever in A, that is passed to the respective port 2 where LEDs are connected. Then I am just introducing the delay, a call delay, that is absolute call to delay. This is unconditional, directly call this subroutine. Okay, then next means LEDs turn, all 8 LEDs turns on with the help of this, and it will remain for 1 millisecond. Then you are putting 00 inside the accumulator, then accumulator data pass to the port, and according to that LED turn off, and it remain off for how much time? As per the delay. And then sjump main again, means again you are remain in the loop, means on off like that. Now we know that delay calculation is done by two ways. One is a software method and second one is a hardware method. Software method is nothing but loop method, and hardware method means using timer. We know that in 8051 there are two timers, timer 0 and timer 1. Now first we will discuss algorithm using software method. Software method means loop method. Now as per the desired time, first you just calculate the count, how much count you want as per the problems, as per the desired time delay. Once you calculated the count, just place that count into the general purpose register. In 8051 there are 8 general purpose register, that is R0 to R7. You can choose any register as per your choice. First place that count into the general purpose register, and every time decrement the count till it is not become 0 to generate that much desired time delay. In this fashion, this is the basic algorithm for delay calculation, and according to that I am just writing the code, that is delay colon, means whenever from the main function we are calling the delay, a call delay, that time cursor will come to this location, that is delay label. Here first value, your first count is placed into one of the register, that is R3. Then second count you are placing into the R5. In this fashion you are taking two general purpose register. Then we are decrementing R5, and every time it is decremented and just check it is 0 or not. When it is suppose it is decremented, means it is initial value is FF, then it's become FE, FD, FC, like that. It is continuously decremented one by one. Okay, and it remained here within this loop only, because decrement and suppose not 0, jump to this label, and this label is on the same line, and that's why your controller will execute this instruction how many times? FF time, that is 256 time. Okay, once 256 is over, that time it coming out of that loop. After 250 time it becomes 0 and it coming out of that loop. Then decrement R3. Now R3 having value 0.5. Now it is it's become 4.04. Again it is checked, it is 0, no. Now it is jump to L1. Again you are putting FF into the R5, again decrement it, and again decrement R3. Means this is your inner loop, it will execute 250 times, and this is outer loop, will execute how many times? 5 times. That is 255 into 5. That much time gets spent to execute this instruction, and that much time delay introduced. and then return. This is a subroutine, means when you are calling a call delay, that time controller come to this delay point, and when return instruction is there, that time it will go back to the main program. Okay, in this fashion we are just writing the delay program. Now this is the demonstration. Now this is your microcontroller. Port 2 is connected to LEDs through this 8 wires. Through this 8 wires, that is P2.0 to 2.7, they are connected to these 8 LEDs. As per when I dump that code into this microcontroller, that time LED will turn on and off by specific time delay. Agree for this? Okay. Now next. Now I will change the problem statement. Okay. Now my problem statement is I want to toggle each group of 4 LEDs. Now we know that there are total 8 LEDs are there. We are just creating 2 groups. One is upper nibble and lower nibble. Nibble means 4. D0 to D3 is your lower nibble, and D4 to D7 is your upper nibble. Now I want to toggle the upper nibble and lower nibble alternately. Okay, with a delay of 1 millisecond. And these LEDs are connected to P2. Now I want to make modification within the algorithm as per my problem statement. My problem statement is what? I want to toggle the group, each group, that is lower nibble and upper nibble alternately. Okay, now first I want to calculate the bit pattern as per this problem statement, and that's why as per my first problem statement, upper nibble is on and lower nibble is off. According to that, 1 is for on purpose, 0 is off purpose. That's why I am placing here 4 1, means your upper nibble become on, and you are placing here 4 0, means lower nibble is off. Okay, means you are just toggling in group of 4, means 4 LEDs on, 4 LEDs off. And second time we are just alternating that pattern, and that time your upper nibble we want off and lower nibble on, and according to that my bit pattern is 0 4 0 4 1. Here your number becomes 0F, 0F, and here your number is F0, but we can't directly place here F0, that's why we are writing here 0. Now I'm just updating the algorithm here. First step is what? Just count program counter, start from the scratch pad. Next, place the proper number bit pattern into the accumulator. Now according to that bit pattern, upper nibble is on and lower nibble is off, means your number is F0. We can't directly place F0 because your number is started with F, and that's why we are writing here 0, because your number must be start with the numerical value. Suppose it is started with alphabet, you must write 0, otherwise your controller will give error. Okay, and that's why I am placing 0F0H into the accumulator. Now third step is from accumulator pass to the port 2. Okay, then give the delay, because we want to see that variation, means upper nibble is on and lower nibble is off. I want to see that, and that's why I'm just introducing the delay in between. Then I will change the bit pattern. After that, what we want to make upper nibble off and lower nibble on, and according to that our number is 0F. Okay, 0F, and then we are just calling the delay, and we are just remain in the loop. According to that, I am just converting algorithm into the code. Okay, now first 3 lines is for passing the program to the scratch pad, which is started at 0030H. These are the common line for all the programs. After that, we started the main program. In the main program, first we are placing desired number, that is F0. But F0 we can't place, that's why 0F0 we are placing into the accumulator. Then pass to the port 2 where LEDs are connected. Then we are calling the respective delay to see that variation. Next time I want to do the other thing, that is lower nibble on and upper nibble off, and that's why we are placing number 0f into the accumulator passed to the port and calling the delay, and then sjump main means you are doing continuously, means it is remain in the loop of upper nibble, lower nibble, upper nibble, lower nibble, like that. This is the delay program that you know. Now third problem statement. In the third problem statement, in the university exam they will ask, write the ALP, that is assembly language program, to display hex counter on LED connected to port 1. Okay, hex counter means it is started from 0 and it must count up to F. Means what we want, 0, 1, 2, 3 up to F. That must be displayed on the LED. There are 8 LEDs that we know. Yes, and that is connected to port number 1. According to that, I am just making the changes in the basic algorithm. First step is remain same. You are started from the scratch pad. Then next step, what we want to start from 0 to F. That's why we are clearing the accumulator first. Then move the content of accumulator to port 1 where all 8 LEDs are there. Means all 8 LEDs remain off. That is initial condition. Then give the delay because we want to see that variation. That's why every time we are calling the delay in between. Then increment the accumulator. Now it's become 1. Then check, is it last digit, that is F? No. Then go back, again increment. Means you have remained in the loop. Every time you are incrementing the accumulator, means initially accumulator is 0, 0, then it's become 1, then 2, 3. Every time it is incremented, and every time we are just comparing with 0f. Is it become last? No. Then again keep in a loop. And every time we are doing that, and then that data passed to the respective port and to display the hex counter. All of you agree for this? Okay. Now we are just converting this algorithm in the code form. The first 3 steps that you know. Okay, then according to the second step, first clear the accumulator. Clear the accumulator means A having now 0. Then next point is data of accumulator passed to the P1. P1 having 8 LEDs. Okay, P1.0 to 1.7. There are 8 LEDs. All data, all 0, all 8 0 passed to this. That's why all LEDs remain off. Then we want to see that, and that's why we are calling the delay. Then increment accumulator. Now value of accumulator is 0, 1. Then next instruction we are writing, compare accumulator with 0f. That is reached to the maximum? No. If now it is 0, 1, and is it not equal to 0f? And that's why this condition satisfied, and that's why I am just jumping to label L2. L2 means here again. Now in A we have value 0, 1. That is passed to the port, means LED now displaying 0, 1. Then call delay because we want to see that. Then increment accumulator, now it's having 0, 2. Okay, again check with 0f. Then suppose it is not equal, jump to L2. In this fashion you are remain in the loop how many times? 15 times. First it will display 0, 0, then it is 0, 1, 0, 2, 0, 3, 0, 4 up to FF. In this fashion we are just displaying hex counter. Suppose in the university exam, instead of hex counter, suppose they are making the change, they want a BCD counter. That time you are just making small change within this program. In BCD counter we want to display a number from 0 to 9, not 0 to F, and that's why in that case I will change only one parameter here. This program, all other program remain as it is. Only change is that here instead of 0f I am just writing here 0a. Okay, means initially 0 will output it, then 0, 1, 0, 2 up to 0, 9, and when it's become again incremented, it's become 0a, and that time both are equal. That time it will come out of that loop. Means it for BCD for decimal counter, for counter it will just it is just counting 0 to 9. That much change is there. Delay program that you know. Okay, then fourth problem statement. Now in fourth problem statement, they demanded write an ALP to display ring counter. Now what do you mean by ring counter? Now for example, suppose one LED is on, then I want to start next LED, then third, then fourth, then fifth. In this fashion, I want to turn on one by one LED from LSB to MSB, and then again from LSB to MSB, means it create the ring. Okay, means one LED is on, after that it is shifted one by one. Okay, after a specific time limit it shifted to next from MSB to LSB again, and it create the ring. Means in this fashion we want to display on the LED, and that's why I will just make the changes in the basic algorithm. Basic algorithm first step remain as it is. We are starting from the scratch pad. Then second step is remain same, clear the accumulator. Clear the accumulator because we have started from 0 0. Then load initial pattern 0 1 inside the accumulator. Okay, then move the content of accumulator to port 1 where LEDs are connected, and that's why LSB means P 1.0 LED will turn on and all other LED remain off. Then give the delay because we want to see that. Fifth step, rotate the content of accumulator towards left or right as per my choice or as per our choice. In that situation, my 1 is shifted towards left or right, and according to that respective LED will turn on, and then that data pass to the port. And then call the delay every time and to display the ring counter on LEDs. Now just convert this algorithm into the code now. Now first three steps that you know. Then first clear the accumulator. Then within accumulator you are placing 0 1. According to that LSB turn on. Outputted that to P1 port. Then call delay because we want to see that. Then rotate left accumulator or rotate right accumulator as per your choice, and you are remain, and then jump to L2 again, just outputted that and keep in loop. In this fashion you are turning on LEDs one by one from left to right or right to left, and it is remain in the loop. Okay, and that's why it is represent as a ring counter. Delay program that you know. Next problem statement is write an ALP to toggle LEDs connected to P1.0 continuously. Now we are not considering all 8 LEDs, we are considering only one LED which is connected to P1.0, and we want to toggle that. Okay, means toggle means you want to turn on and off. Okay, and we are just concentrating now on a single LED, not all 8 LEDs. Okay, and we want to introduce the delay of 100 microsecond with the timer 0, mode 1 and interrupt structure. Means we are not introduce delay with the software method. Here directly they are mentioning timer 0, mode 1. Okay, and that's why we must use the hardware method. Okay, according to that I will just make the changes within the program. First initialize the program counter from the scratch pad, then continuously toggle the LED which is connected to 1.0 by the instruction complement P1.0. Suppose it is 0, it's become 1. Suppose it is 1, it's become 0 with the help of complement instruction. Okay, after interrupt arise. Now we know that delay calculation with the timer 0, mode 1. Yes, now we just recall that. Now in timer 0, mode 1. Okay, mode 1 is 16-bit timer. Okay, it is just varying from 4 zeros to 4F. Okay, now this is timer having two section, a lower byte and higher byte, that is X is either 0 or 1. In our problem statement they are mentioning timer 0, and that's why it is TL0 and TH0. Now clock source for timer is coming from the crystal. For timer it is coming from the crystal. For counter it is coming from the external events. Yes, now we are considering as a timer, and that's why in clock source is coming from the crystal. In during practical time, practical crystal having value 11.0592 megahertz. It is divided by 12 because it is 8051, and that's why as per the architecture crystal frequency divided by 12, and according to that we are just getting here clock signal whose frequency is 921 kilohertz and time duration is 1.085 microsecond. Okay, now these clock pulses are here, but it is not reach up to the timer. When you are giving the start command, that time when you are set bit TR1, that time this become this input of one of the input of AND gate become 1, and that time this AND gate will pass these clock pulses to timer section, and timer start counting from initial value whatever you want. You are just calculating that initial value and you are placing here. Now this timer start counting from that initial value up to maximum value, that is 4F. When one more pulse is coming, it will overflow, it will set the flag, and it's roll over to all zeros. In this fashion we just know that all this timer section. We know this algorithm for programming of timer. First we are calculating T mode value as per which timer you want to use or which mode you want to use. According to that we are just calculating T mode value. Which timer we want to use, that is timer 0. Which mode you want to use, mode 1. You want to use a software method or hardware method to turn on the timer, software method. In this fashion we are just calculating the value and we are placing into the T mode register. Then next we are calculating the initial value and you are placing into the respective register, that is TL0 and TH0. Okay, now how to calculate this initial value? For that we know the formula. Okay, then just calculate that formula, just calculate that value and place here. Then start the timer. Next step is what? Continuously monitor the flag bit. Respective timer flag become overflow or not. Okay, suppose it is overflow, then stop the timer, clear the flag, and again remain in the loop. That is the basic steps related to timer section that we know. Now we know we want to calculate the numerical value that we want to place into the TH0 or TL0, and as per the problem statement. My problem statement is I want to generate the time delay of 100 millisecond. My crystal frequency is 11.0592 megahertz. We already know this problem statement, but I'm just recalling that. According to that crystal frequency, I'm just calculating the timer frequency, that is crystal frequency divided by 12. It is coming 921.6 kilohertz. Its time duration is coming 1.085 microsecond. Then in first step we are dividing the desired time delay by timer clock duration, that is 1.085 microsecond, and that's why we are just getting the answer, that is 92. When you are dividing the desired time by 1.085 microsecond, and that time I am getting the answer 92. In the second step we are subtracting this 92 from the maximum value. Your mode 1 is 16-bit mode, and that's why maximum value is 4F, and 4F decimal value is 65536, and that's why 92 is subtracted from that, and that's why we are getting the answer 65444. Just convert that into the hex. Its value is FFA4. FF is higher byte and A4 is a lower byte, and that's why you are just placing that into the respective registers. Now we are calculating that initial value, we are just placing that, and according to that we are just writing the program. Okay, now first three steps that you know, because we want to start from the scratch pad, and that's why we have started from 0030H. Here main program start. First you want to use which timer? Timer 0, and that's why we are just calculating the number timer 0 mode 1. Okay, according to that and software method we want to start the timer, and that's why the number is 01, and that number we are placing into the T mode value. Then as per your calculation, higher byte is FF and next byte is A4. You are placing into the respective register, that is AH0 or AL0. All of you agree for these three steps. After that I want to write the code as per the interrupt structure, and that's why I must enable the interrupt. Okay, and that's why I am enabling the interrupt with the help of IE register. That we know that this is your, I will again recall that interrupt structure. In interrupt structure, interrupts are enabled with the help of RE register. Now this is the structure for RE register. We already covered this part during interrupt structure of 8051. Okay, now here RE register, that is interrupt enable register, is 8-bit register. Here each bit having some specific meaning. Now first bit, that is MSB EA, that is enable all. Okay, that must be 1. Suppose it is 1, that time your interrupt pass to the controller. Suppose this is disable, even interrupts are individual interrupts are enabled, no use, it will not reach up to the controller. That's why EA must be 1. Okay, and all other interrupts, that this is interrupt related to timer 2, it is not related to 8051, it is related to 8052. Okay, interrupt related to serial communication, interrupt related to timer 1, external interrupt 1, external interrupt 0, we are not interested within. That's why we are placing here 0 0 0 0, all other are 0. Only I am interested in timer 0 interrupt, and that's why I am just enabling it, and according to that my number is 8 and this is 2, that is 82. All of you agree for this? I am just enabling overall interrupts. All individual interrupts are off except timer 0 interrupt, and that's why my number is 82, and that 82 number I am placing into the RE register. Okay, now start the timer TR0 with the help of instruction set bit TR0, and then sjump start, means it remain in the loop. Whenever interrupt coming, it will go to the interrupt vector table. Okay, now we know that interrupt vector table. Now this is interrupt vector table. We know that there are 6 interrupt sources, that is reset, interrupt due to the hardware interrupt, INT0, INT1, timer 0, timer 1, or serial interrupt. Each one having specific location inside the memory. Now for interrupt related to timer 0, its location is 40B, and that's why we are jumping to this location when a interrupt of timer 0 is coming. That time microcontroller just pass to which location? 430B location. That is this is extra, this is 430B location, and at that location we are just writing the program as per my problem statement. In my problem statement, I want to complement the LED which is connected to the 1.0, means I want to toggle the LED which is connected to P1.0. That's why I'm just writing the instruction CPL P1.0. That's why the LED which is connected to 1.0, that get toggle. Once it is 1, it becomes 0 0, then it will become 1, like that, and then return I. Every time it will interrupt generate, it come to this location, it will complement it output, and it is coming back. In this fashion it remain in the loop. In this fashion we are continuously toggling the LED. Yes, this cover your LED interfacing, and this is your second practical. During practical duration I am just demonstrating this on a hardware kit.